There is a material stronger than steel, lighter than plastic, and, at the scale of a single strand, a better conductor than copper. We discovered it over 30 years ago. Almost no one uses it. The reason why reveals something true about every miracle material ever announced, something the hype cycle has never been honest about. This is not a story about science failing, it is a story about the gap between knowing something is possible and being able to do it, between a measurement in a lab and a product in the world, between a discovery and a civilization that can actually use it. This is the story of carbon nanotubes. And by the end, you will not just understand why this material has not taken over. You will understand why that answer keeps repeating with every wonder material, every generation, on a loop we still have not broken. The hype was real. In the late 90s and early 2000s, there were magazine covers, television specials, and conference keynotes from serious scientists using the word revolutionary without irony. Venture capital moved and government programs launched. The material was described repeatedly as having the potential to restructure entire industries. Not one industry, but all of them. For a long moment, it felt like the future had sent us a preview. The question is why the preview never became the movie. Not because the science was wrong, it was not. But the science was only half the story, and the other half barely got mentioned. The promise was not incremental. It was civilizational. Aircraft would shed weight in ways that transform fuel economics. Aviation fuel is roughly a quarter of an airline's operating costs, and weight is the primary driver. A material 10 times lighter than steel at the same strength does not move the needle, it moves the entire economics of the industry. Bridges could span distances no steel structure could touch. And then there is the application that sounds like science fiction but is grounded in physics understood for over a century. The space elevator. A cable stretching from Earth's surface to geostationary orbit, 36,000 kilometers straight up, held taut by Earth's rotation like a ball on a string. You attach a climber and it rides up. No rocket, no re-entry. The energy cost of reaching orbit drops by orders of magnitude. A kilogram of cargo currently costs roughly what a kilogram of gold costs to launch. Space stops being a destination for governments and billionaires. The reason it was impossible was not the concept, it was the cable. The leading engineering designs require a tensile strength of around 100 gigapascals, more than 40 times the best steel. Even the best carbon fibre falls an order of magnitude short. Then someone ran carbon nanotube numbers through the calculation, and the number worked. Not approximately, exactly. A material so far outside the normal range of what we build with that it makes previously impossible things suddenly physically legal. Carbon is one of the most promiscuous elements in chemistry. It bonds to itself in more ways than almost anything else on the periodic table, and each arrangement produces something dramatically different. Graphite, the soft black material in a pencil, is carbon. Diamond is carbon. Same element, completely different structure, completely different properties. In 1985, a team of chemists vaporized graphite with a laser and found a molecule made of 60 carbon atoms arranged in a perfect sphere like a tiny soccer ball called Buckminster fullerene, or the buckyball. It won the 1996 Nobel Prize in Chemistry, and it cracked the field open. If carbon could form a perfect closed sphere, what other geometries were possible? That question was still hanging in 1991 when Sumio Iijima, a Japanese physicist at NEC Research Labs, sat down to study residue from carbon arc discharge experiments. Iijima had a reputation for looking carefully at things other people considered unremarkable debris. Under the electron microscope, he found tiny hollow cylinders with walls just a few atoms thick, made of nothing but carbon. He characterized them, measured them, and published the results in Nature. It is worth noting that Iijima was not the first to observe carbon filaments. Morinobu Endo had studied carbon nanofilaments in the early 1970s and published images in 1976 that almost certainly contain what we now call multi-walled nanotubes. Carbon whiskers had been spotted in various experiments for decades, glimpsed by people who did not have the context to understand what they were seeing. This is how discovery often actually works. Not a single eureka moment, but the same thing noticed repeatedly by people who lack the framework to recognize it, until finally someone does. What Iijima did was recognize what he had, characterize it rigorously, and publish in a way that gave the rest of the scientific world the tools to follow. He did not just find it, he made it findable. That is what set off the chain reaction. You've probably heard of graphene, a single layer of carbon atoms arranged in a flat hexagonal lattice, like chicken wire scaled down to individual atoms. Roll that sheet into a seamless cylinder. That's a carbon nanotube. No seams, no joins. A single-walled nanotube might be 1 nanometer across. A human hair is 80,000 nanometers wide. The tube is so narrow that visible light waves are too large to interact with it in the usual way. The carbon-carbon bond in that lattice is one of the strongest in chemistry, the same bond that makes diamond the hardest natural material on Earth. And crucially, there are no grain boundaries. When you look at steel under a microscope, you see it is not one continuous crystal. It is a mosaic, millions of tiny crystalline regions meeting each other at seams. Those seams are where stress concentrates, where cracks begin, where fractures propagate. What fails is not the material itself. It is the seams. A carbon nanotube has none. One molecule wall to wall, no seams to fail, now the numbers. Mechanically, structural steel sits around 400 to 500 megapascals of tensile strength. High-grade aerospace alloys reach maybe 2,500 megapascals. Individual carbon nanotubes have been measured at 25 to 66 gigapascals, with near-defect-free tubes approaching 100 gigapascals. 20 to 40 times stronger than the best steel, at roughly 1/6 the weight. Electrically, the chirality, the angle at which you roll the graphene sheet, determines whether the tube is a metal or a semiconductor. Roll it one way and electrons flow with almost no resistance, carrying more current for its size than copper wire. Roll it a slightly different angle, a few degrees, and you get a semiconducting material you can build a transistor from. Same atoms, same bonds, same chemical composition. Different geometry, baked in at the moment of synthesis, determines everything. That is not how materials are supposed to work. Thermally, individual nanotubes have been measured at heat conductivities exceeding 3,000 watts per meter Kelvin. Diamond, which held the bulk materials record, reaches around 2,200 watts per meter Kelvin. For electronics that generate enormous heat in tiny spaces, this is not a minor advantage. It is the difference between a device that runs and one that throttles itself into uselessness. 3 properties: strongest material, best conductor, better than diamond at moving heat. Materials are not supposed to win every category simultaneously. Hold on to this, at the scale of a single tube in a controlled experiment, because everything else in this story hangs off it. Making one perfect nanotube is difficult. Making 1 billion of them, the same length, the same chirality, assembled into something you can hold in your hand, is an entirely different challenge. And that challenge is what 30 years of work has failed to fully solve. Synthesis. You grow nanotubes by flowing carbon-rich gas over metal catalyst particles at high temperatures. What comes out is a chaotic mixture. Different lengths, diameters, chiralities, some metallic, some semiconducting, some multi-walled. Tangled with amorphous carbon residue and catalyst particles you do not want. Sorting this is like separating wet spaghetti by strand length, except you cannot see the strands. Some conduct electricity and some do not, and each one is 1,000 times thinner than a human hair. Defects. Real synthesis produces real imperfections. A missing carbon atom, a bond in the wrong configuration, a spot where the lattice kinks. A single defect in a tube thousands of atoms long can cut its measured strength by more than half. Underload, all the force routes through the weakest point, and the floor fails. Alignment. A nanotube's extraordinary strength exists along its axis. For a strong cable, every tube needs to point the same way. The math is punishing. A tube at 30 degrees off axis contributes only 75% of its strength. At 45 degrees, you are down to 50%. Billions of tubes drifting slightly in their own directions, and your theoretical material rated at 66 gigapascals becomes something far more modest. Cost. High-purity single-walled nanotubes, the quality level where the extraordinary properties emerge. still run hundreds of dollars per gram. These are not four separate problems, they are four faces of one. The gap between what you can demonstrate with one tube and what you can manufacture with 1 trillion. The gap is self-reinforcing. Improve one and the others are still there, demanding. The best nanotube fibers made today, a 2024 result in Science reported static strengths of 8.2 gigapascals and dynamic strengths reaching 14 gigapascals, beat the best commercial carbon fiber by a meaningful margin. The theoretical ceiling is an order of magnitude higher. Most of the performance disappears in the translation from nanoscale to macroscale. While structural applications struggled with scale, a completely different industry was watching for a different reason: the electronics industry. That promise is still live. It starts with a problem called the end of Moore's law. For 60 years, the semiconductor industry advanced by making transistors smaller. Gordon Moore first observed in 1965 that the number of components per chip had been doubling roughly every year, and that was later revised to every 2 years. The rate was so consistent it became the organizing principle of an entire civilization's worth of digital technology. Every 2 years, something that required a room-sized machine could fit on a desk, then in a pocket, then on your wrist. The problem is that transistors are now so small, features measured in single-digit nanometers, that silicon is bumping into the limits of physics. At these scales, electrons do not stay where you put them. They quantum tunnel through barriers they are supposed to be blocked by. The insulating layers between transistor components are now just a handful of atoms thick, and a handful of atoms is not a reliable insulator. Current leaks through constantly, even when the transistor is supposed to be off. That wasted current becomes wasted heat. And the transistors themselves, crowded so close together, interfere with each other in ways that get harder to manage with every generation. The free performance dividend from transistor shrinkage is ending. Nothing in silicon's toolkit can obviously replace it. Carbon nanotubes entered that search compellingly. Nanotube transistors switch faster, run cooler, and can be made smaller while still working correctly because the quantum effects that plague silicon at scales below 10 nanometers are different and more manageable in carbon. IBM researchers demonstrated nanotube transistors that outperform the best silicon devices at the same gate length. Manufacturing is the problem again. A modern processor contains tens of billions of transistors. A single metallic tube in a semiconducting array causes a short circuit that destroys the device. You would need to place tubes on a wafer surface with the orientation, density and consistency of a modern photolithographic process, competing with a silicon industry that has spent 70 years optimizing. None of those things exist yet, but the physics advantage grows as transistors shrink. The moment when silicon simply cannot go further is approaching. Whether nanotubes are ready when that moment arrives is the open question. In the late 1990s, NASA published technical studies on space elevator feasibility, with nanotube cables at the center. DARPA ran cash prize competitions for cables meeting specific strength thresholds. The only question, many researchers believed, was when. Consider what happened to one of the most serious attempts to answer that. Nanocomp Technologies was founded in 2004 by Peter Antoinette and scientist David Lashmore, spun out of a New Hampshire technology development company. The pitch was direct: take the lab results seriously, build the manufacturing process around them, and deliver nanotube fibers to aerospace and defense customers at commercial scale. No hand-waving about future breakthroughs, just execution. To get it started, Antoinette took out a second mortgage, signed up for every credit card application that came his way, and did not take a salary for 2 years. The Valley of Death has a human cost the hype cycle never mentions. This is what it looks like. They raised tens of millions of dollars, built a large manufacturing facility in Merrimack, New Hampshire, and landed real government contracts, including an $18.5 million deal under the Defense Production Act. Their material flew on NASA's Juno spacecraft to Jupiter. By the mid-20-teens, Antoinette could put wire, rope, sheet material and a protective vest on a conference table and say, "This is in satellites, ships, soldiers, aircraft." That's genuinely impressive. That's product in real applications. And yet the structural revolution never arrived. The manufacturing wall held. In 2018, Nanocomp was acquired by Huntsman Corporation and absorbed into their Advanced Materials division. A real outcome, just not the one the original pitch had described. And that arc, from genuine lab breakthrough to serious investment, to the hard manufacturing wall and a pivot toward a sustainable niche, repeated itself across the industry. The science was not wrong. The timeline was catastrophically wrong. This is what the hype cycle consistently gets wrong. Press coverage of a new lab result treats the result as the endpoint. What it actually proves is only that the principle is sound, that one tube in one experiment behaved as the physics predicted. Whether that principle can be translated into a manufacturable process is a completely separate question, a harder question, one that almost never makes the press release. And here is the structural reason this keeps happening. The funding system requires excitement. Excitement requires overclaiming. The gap between what scientists can honestly promise and what funders need to hear is where unrealistic expectations are born and where years later the recriminations follow. It is not a conspiracy. It is an incentive structure that has been running on the same loop for decades. The fix is not cynicism about science. It is a simple demand. Separate the discovery announcement from the manufacturing roadmap. Tell us what the physics allows and what the process currently delivers in the same breath, at the same volume. That is not pessimism. That is the full story. The pattern is older than nanotubes. Titanium should have taught us this lesson in the 1950s. By then, engineers understood it was categorically better than aluminum, stronger, more corrosion resistant, and better at high temperatures critical for jet engines and airframes that had to endure sustained supersonic flight. The material science case was unambiguous. Titanium was going to reshape aerospace. What nobody had adequately reckoned with was how brutally difficult titanium is to work with. It reacts with oxygen and nitrogen at high temperatures, which means welding requires inert gas shielding and specialized equipment that did not yet exist at scale. It work hardens rapidly during machining, dulling cutting tools at rates that make it expensive to shape. It is prone to catastrophic failure if processed incorrectly, which meant that every manufacturing practice developed for aluminum and steel had to be rethought from scratch. The engineers who were certain titanium was about to transform aviation were right about the material and wrong about the timeline by decades. Titanium did find its place, but only in applications where its advantages were decisive enough to justify the premium. It never replaced aluminum because aluminum's manufacturing ecosystem, cheap, mature, and well understood, was simply too good. Superconductors made the same promise in 1986 when Bednorz and Muller announced superconductivity in a ceramic material at temperatures reachable with liquid nitrogen. The Nobel Prize came the following year, the shortest gap between discovery and prize in the history of the physics Nobel. The vision was intoxicating: power lines with no resistive loss, motors and generators of unprecedented efficiency. MRI machines and Japanese maglev trains use superconducting technology today, but the power grid is still copper nearly 40 years later because making high-temperature superconductors into long, flexible, mechanically robust cables that can be manufactured reliably at scale required solving engineering problems the lab discovery said nothing about. The material worked, the process never caught up. Graphene. Isolated in 2004, Nobel Prize in 2010, same billions, same hype. Today, real applications in batteries and composites, transformative applications, still waiting. There's a name for the gap where materials go to disappear, the Valley of Death. It is the space between laboratory demonstration and commercial deployment where most promising materials fail, not because the science was wrong, but because manufacturing never caught up. The Valley does not care how impressive the physics is. Materials do not win simply because they are better. They win because they are better enough at the right cost, at the right scale, at the right time, and because the entire ecosystem around them is ready. Steel is not the strongest material we know, but it is cheap, abundant, and weldable, so you can join pieces of it on a job site with equipment that fits in a truck. An entire civilization's worth of infrastructure was built around steel over centuries through Real failures, bridges that fell, buildings that cracked, ships that buckled, and those failures became the codes and standards that govern how steel is used safely. Displacing steel does not just require a better material, it requires rebuilding all of that, the manufacturing ecosystem, the workforce knowledge, the supply chains, the codes, the design tools, and the testing standards. That is not a materials problem, it is a civilization infrastructure problem. Silicon is not the best semiconductor. Germanium has better electron mobility. Gallium arsenide switches faster. Carbon nanotubes outperform all of them at the atomic scale. But silicon comes from sand, and the industry spent 70 years learning exactly how to work with it. You can buy silicon wafers today at atomic level consistency, in industrial volumes at predictable prices from dozens of competing suppliers worldwide. Beating silicon in a lab demonstration is not the same as beating silicon in the world. It is not even in the same category of achievement. The more accurate picture of carbon nanotubes today is not defeat. It's a radical material that found its way into real applications, just not the ones anyone predicted. The most commercially significant use is in battery electrodes. Carbon nanotubes thread through the electrode structure of lithium-ion batteries, including those in electric vehicles, as a conductive additive. Alignment does not matter, chirality does not matter. The performance improvement is real: better conductivity, longer cycle life, improved charge rates. There is a reasonable chance carbon nanotubes are already in the battery powering your car. Just not in the dramatic structural role anyone would have predicted in 1995. The applications that work are the ones where requirements are loose enough to accommodate what manufacturing can actually deliver. The applications that have not arrived, load-bearing cables, structural beams, high-performance computing chips, require synthesis, perfection, chirality control, and alignment solved simultaneously at large scale, at low cost. That intersection has not been reached. What's actually happening now, 30 plus years after Ijemar's paper? Real progress, real remaining obstacles. A timeline nobody should state with confidence. That 2024 paper in the journal Science, reporting 8.2 gigapascals static and 14 gigapascals dynamic, is significant not just for the numbers but for what produced them. New assembly methods include wet spinning processes borrowed from the carbon fibre industry, post-processing treatments that coax tubes into better alignment, and surface chemistry that improves load transfer between tubes at contact points. The alignment problem, which for so long seemed fundamental, is starting to look like an engineering challenge with engineering solutions. When a problem looks like physics, it might be a wall. When it looks like engineering, it is a slope. Slopes are hard to climb, but you can climb them. The space elevator still requires roughly 100 gigapascals. Current fibres deliver 8 gigapascals. The researchers who study it do not call it permanently impossible. They call it contingent. Permanently impossible means the physics does not work. Contingent means the physics works fine. And the question is engineering. The first closes doors, the second leaves them open. The lab result proves the principle. It does not prove the process. And the process is where materials live or die. Carbon nanotubes are not a failed story. They are in the battery of an electric vehicle right now, improving its performance in ways that are measurable and real. They are in research labs where problems that seemed intractable a decade ago are slowly coming apart. Not dramatically, not with a single breakthrough, but through the steady accumulation of incremental advances that eventually add up to something you can hold in your hand. The people who have spent their careers in that gap know what it costs. In time, in money, in expectations set wrong from the beginning by people who understood the science but underestimated everything that follows it. Antoinette's second mortgage, the years without a salary. Multiply that by 100 companies, 1,000 researchers across 30 years. That's what the Valley of Death actually costs, not just in capital but in human lives, routed toward a problem the world expected to be solved in 5 years. The hardest part of the work is almost never figuring out what's possible. It is figuring out how to make 1 billion copies of it reliably, affordably, at the scale the world actually needs. Some of the people who have spent their careers in that gap believe carefully, based on specific progress on specific problems, that the crossing is getting closer. Maybe they are right, but honest is the right word, and after 30 years of miracle material announcements that did not land on the promised schedule, honesty is exactly what the conversation needs.